Hello, we are Okstate01, and we decided to tackle the identification of atomic resolution defects in STEM images. A study this year actually published from the Russian Academy of Science found that less than 2% of all TEM images are actually published, and part of that is due to the, basically the overhead cost of just the time that we have to spend manually masking everything and processing it. So we decided to attempt to do that with a convolutional neural network.
Our approach accurately labels defects in STEM images using an ensemble method of convolutional neural networks. So here we have an example STEM image, and then here we're just going to label one particular type of defect at the moment. So we're just going to label a stacking fault. So here is the raw output of our system. Right, and you can see it very accurately labels the region in which the stacking fault is present. So how does our model accomplish this? So it starts with a series of preprocessing steps. So our model chops up the image into smaller windows, which it then uses to actually classify. So we start with the raw data, and then we normalize across the whole data set so that the magnitudes are similar, and then we apply a blur to cut down on the noise, and then we do a Fourier transform, and then we do some thresholding on our Fourier transform. So this gives us our final input to the model. So like I said before, the model is an ensemble of convolutional neural networks. So each of the different defects has their own model. And this has a couple advantages. It means that we can train more specific models for different kinds of defects. It means that the models can be smaller, they run faster, they train much faster. Everything was trained on a CPU. Yeah, and so it's very easy to change out different models that are perhaps underperforming without affecting the performance of the entire system as a whole. Here we have our model architecture. Our model architecture is comprised of a series of convolutional layers, which is then followed by some dense layers to process and output the final classification. So there's some number of these models for each feature, and as we looked before at our example image, we're now going to classify, we're going to go through the classification of this fault and in more detail and about what the model does, and then we'll look at the full classification of the image. So like I said, this is the raw output. But there's a bunch of noise in this image, so we use kind of a heat mapping method. So we look at the area where the prediction is the densest, and we use this to actually get that region of the image. And so this is what it kind of looks like as a highlight on the image. And we can apply this to, it's more visible in better color here, but we can apply this to all of our defects, right? So we have stacking fault here, a stacking fault here, an LC right where they meet, and then a twin boundary down at the bottom. And the rest of our lattice is crystalline perfect. Yeah. Additionally, the model, the CdTe was performed quite well, but the STO is very hard to judge due to limitations with the data. However, my colleague here, I don't know.
Yeah, that's fine. Yeah, the data we have with STO was highly crystalline, that had no defects in it, and obviously it won't be showing the defects in the image. But we tried this train model with another image we have from STO, which was defect-rich, and then it worked well on that. Yeah, and that means it's working good for the STO2. Thank you.
Thank you.